Okay, let's work on this last script of the module, script 8 on trend analysis. We'll run the script. This script takes our chirps data, aggregates it to a monthly data set or yearly data set with the seasonal rainfall. So this is looking at the season each year, June to September, and computing the total rainfall that happened in each rainy season for each year from 1981 to 2020. And finally, we can plot a time series at a single location. So we have this image, which is the year image collection having yearly images of the seasonal rainfall for each year. And we can plot the time series at a single point, and we can plot this chart. And this is what this looks like. Now, if you look at this, it says in 1981, this was the rainfall. In 1983, this was the rainfall, and so on. Now, visually looking at it, can you say, is the trend of the rainfall increasing, decreasing, or staying the same? I want to quantify. At this pixel, are we experiencing increased rainfall or decreased rainfall? What's the trend here? And to answer that question, quantitatively, we can apply different techniques. So let's learn what are the different techniques that can answer this question for us. So this is our time series. And we want to answer the question, is the precipitation increasing, decreasing, or staying the same? And we want a quantitative answer. There are different techniques for doing this. They are classified into different ways. When you are doing trend analysis, you need to look at different parameters. Do you have a single trend or a seasonal trend? So do you have a monotonic trend? That means it's increasing year to year, or it kind of goes through a yearly cycle. An example of this would be, say, precipitation would be a monotonic trend. It's either increasing, decreasing. It doesn't really have a yearly cycle. If you consider vegetation, for example, crop will have a yearly cycle and also a trend over time. So if you want to compare the trend of vegetation or a crop, is the yield going up or down? You will see that the trend would be, there'll be an inter-annual trend where it increases in the growing season. When there's harvest, again, the NDVI decreases, and then that peaks and valleys would kind of increase or decrease over time. So that has a seasonal trend, not just a single trend of that. Yes, good question. So precipitation is also a seasonal change. If you look at the yearly precipitation, that's not a seasonal trend. So if you aggregate it to yearly, then you can consider that as a total rainfall in a year or a total rainfall in monsoon. And you compare that year over year, that's a monotonic trend. Trend, does any of the factors affect the trend? In our case, we plotted the precipitation against time. And is the time the only factor? Or maybe there are other covariates. Maybe temperature is affecting that. Maybe other parameters, that might be affecting the trend of that. So you need to consider that. If it's just a single variable like time, you can apply a different technique. If you have covariates, you have to apply other techniques such as linear regression. And then finally, what technique to use? There are two classes of techniques, parametric and non-parametric techniques. We'll learn about this in detail. So parametric methods are kind of the methods you learned in statistics. So these methods employ the statistical techniques that assume that your data has a normal distribution. The most statistical technique assumes some knowledge of the distribution beforehand, and then you can apply this technique. So if you say, I want to do some regression, you need to say, oh, my data has a normal distribution. And that's an important assumption that most statistical technique will be. This techniques, the advantage of this, that you have a small sample, they are still robust for that. They are sensitive to outliers, but you have a small sample, you can still get a decent trend out of it. And also they are popular because they require less computation. They are fairly simple to compute and can be computed even by hand if you wish to. On the opposite side, non-parametric methods are another kind of methods which assume no distribution. You can just use them on any kind of distribution. You don't need to have any knowledge of that. It's also more robust against outliers. But on the contrary, you need long time series. If you have a very short time series, these methods are not very robust. Also, they require a lot of computation, but with Earth Engine, that's point is not really valid because we have a lot of computation, but they require far more computation than the parametric methods. What are the different parametric methods that you have? You have linear regression. So you have some covariates and you want to predict the variable based on the dependent variables. So you have an independent variable or one or more independent variables. You have one or more dependent variables, and you can find the coefficients and build a regression model. Earth Engine supports linear regression. You can do per pixel linear regression, and it supports many different techniques for doing linear regression. Harmonic modeling, you can do seasonal trends. So you have a time series of NDVI, which has the seasonal trends, and you can actually fit a curve to and find the model that describes that curve. So you can actually fit a sine wave to that and say, these are the amplitude and phase of that particular time series. And you can use that to model the time series. So this is quite used in modeling, say, NDVI time series, vegetation time series, and doing yield modeling and so on. There are also other techniques, not a simple model, autoregressive models you take for each step in time. You build a separate model based on the history at that point. And then as you get more data, you can update your model. So again, it's a more adaptive models based rather than a single model to describe the entire time series. This time series techniques are again quite advanced, but there is a really nice video tutorial by Nick Clinton in the user guide. I've linked to that. So if you want to do linear regression, if you want to do autoregressive modeling or harmonic modeling, do check out this tutorial where he explains the concepts and it comes with the code to do this. We're going to cover non-parametric method. They are simpler to implement than the parametric methods. And again, we do not need advanced statistical knowledge to implement this. And we'll work with some reducers that come in with Earth Engine to implement those. If you've heard of this methods, Mann-Kendall, sense-slope, these are the non-parametric methods to do trend analysis. The Mann-Kendall test is a useful test to determine whether there is a trend at the pixel or not. And the way this is done is you take the time series and you simply take each point in the time series, compare it against the previous points, and check if it's higher or lower than the previous point. And you keep track of that. At the end, if your output comes out to be positive, you can say, oh, there's a positive trend. If the output comes out to be negative, you can say it's a negative trend. So visually, you can think of it like this. Let's say you have a trend like this. You take each value and say, compare this against the previous value. Oh, this is higher than this, so I'll keep it +1. Then I take this value, compare against the previous one. This one is lower, so I'll do -1. Take this, compare against this value. Oh, this is higher than this, so I'll do +1. And you keep doing this for every point, compare against all previous points. Keep a tally of positive and negative. At the end, whatever you're left with, if it's positive, that means at that point, it's a positive trend. It's a useful test to quantify if there is a trend at the particular pixel or not. We have a script implementing this in your supplement. We're not going to cover this in detail, but I'll show this at the end. We're going to cover the counterpart to this is a sense slope, which will not only tell you whether it's increasing or decreasing, but also tell you the magnitude of the trend. This is more useful things and saying that, oh, there's a trend of 10 millimeters per year increase at that pixel. So you know that there's a magnitude to that trend as well. Very similar technique as what we saw previously, where instead of just computing positive or negative, you actually compute the slope of the line. For each point, connect to the all previous points, compute the slope, keep a tally of this, and at the end, the final value is the slope of your final time series. So similarly, if I show you visually, you have a time series like this. You take this point and say, what's the slope of this point against this point? Okay, this is the slope. So you say, this is my +x. For this, you compute the slope against this line. You can say, this is my slope. You say, this is -x2. You compute for this point, trend against this thing, and you say +x3, right? And you do this for every point in your time series, compare the slope against all the previous points, and what you're left with is your final output. Earth Engine has a reducer called EE reducer sense slope that can be used to compute the sense slope at every pixel. One of the advantages of the setup in Earth Engine with reducers is that you can do a per pixel trend. This is not possible in other software. In other software, you have to do this at a polygon level. So you have to aggregate this at some polygon and then say, I will use that some tabular methods to do your statistical operation. Here, you can do it per pixel. That means now we'll create a global map of precipitation trends just using a few lines of code in Earth Engine. And of course, if once you have your final trend, you can do reduce regions to compute average slope in a region or average trend in a region if you wanted to. Let's see the process of computing sense slope. It's going to use a reducer. So you have your yearly images. So first we'll take our source data set, create yearly precipitation. So we have 40 images. Each image is the total rainfall for that year. And at each pixel, you know the total rainfall at that particular year. And now you take this time series at each pixel and you say reduce it using sense slope reducer. This reducer is a 2-input reducer. All the other reducers we have seen so far are 1-input reducer. That means you have one band of image and you can get some statistical output or your list of values and you get the values. In sense slope, you need 2 values. You need the value of precipitation, plus you need the time. You need to know the year and the precipitation. So you need 2 inputs and then only you can get the trend. So you can say in 1980, this was the precipitation. 1985, this was the precipitation. 1990, this was the precipitation. So you need the time along with the value. So you give both as input and you will get the final value as the slope. So you need to compute these 2 values. The way to do this in Earth Engine, since we are working with images, instead of having a single band image with precipitation, you need to create 2 band images. You need 1 band of precipitation value and 1 band of time. And you have those 2 band images at each time step. You do the reducer, then at each pixel, you'll get your output from the reducer. And again, the output will be 2 things. You will get the slope and intercept, the sense slope. So the slope will be the magnitude, and intercept will be the offset that you get by fitting the trend line to it. Okay, so let's implement this. Once you learn how to do this, you will be able to implement all the other regressions in Earth Engine. So linear regression works the same way. Harmonic regression works the same way. You need to create a multi-band image, and multi-band images, they are your covariates. And you have an image collection of multi-band images, and then you fit your linear regression at each pixel of each image. Okay, so let's implement this in Earth Engine, and we'll see the output. So far, we have created this yearly collection. We have 40 images. Each image is the monsoon precipitation for that particular year. So I have a property called year, which is for that image, and you have 1 band of precipitation. This is what we've done previously as well. We've just created a function that takes the year, filters the data for that year, computes the total precipitation, returns that. And we have mapped that function over the list of years from 1981 to 2020. So we have 40-year time series, and now we want to compute the sense slope from this time series. So first we need to prepare our data. So remember, we need to have 2 bands. We just have 1 band here. We just have precipitation. We just need to have 1 more band of each image, which represents the time of that particular image. So I'll write a function. This will be a function that takes image as the input and returns another image. Now, going back to this diagram, we need to, for each pixel, we need to know the precipitation. We already have that. For each pixel, we need to know the time of that pixel. Now, the time of each pixel in every image is the same, right? It's the year, whichever year we are computing that precipitation for. So if this image was 1980, all pixels has to be 1980. So if we create an image where all pixel values are the value of that year, add it to this image, then we have this two-band image where one band is the precipitation at the pixel and second band is the year value at the pixel. And why we need an image band? Why can't we have a property? Because the reducer runs at each pixel. It's going to pick up the pixel values from all images at that particular location and get those 40 values and send it to the reducer. And those 40 needs to be pairs. So you need 40 pairs, year, precipitation, year, precipitation. And when you have those 40 pairs at each pixel, then only you can get the output of the trained. So to process this, we need to add a new image, a new band to this image, which is the year value of the year. So first, let's get the value of the year. We have already saved this as a property called year in the image. So you can see we have a property called year. So we just got that as a number. And now we have a number. Earth Engine has a helper function to create a constant image. We just create an image where all pixel values are the same number. So we'll use this and say image dot constant. And we'll just say, use this as the year. And again, we can convert this to number so that this value is a number. So when you look at this image into map, all the pixel values will be just the value of the year, 1981, 1982, whatever. And we create a two-band image. So we'll create our image. So we'll say our result image will be, we can use this function called image cat. This cat stands for concatenate. This is terminology that says join two things. So you take multiple images and you put them together in a single image as bands. So this is what this function does. And we can give it a list. So we have our year image and we have the image itself, right? So we have two values here. The original image is the precipitation image. This one is a constant image. We put them together as two bands. We'll get two-band image. First band is a year. Second band is a precipitation. And just for clarity, we'll just rename this. And we'll just rename this to be year and PRCP. So we'll have two bands. First band is the year band. Second band is the precipitation band. And we can return the result image. Let's apply this to our collection. We'll take the yearly collection, map this function. And let me just print. So we had an image collection of 40 images, one band images. What we get is 40 images with two bands. Each image has a band of year and a band of precipitation. The second image also has a band of year and precipitation. Okay, so this was the pre-processing that we did, where we created a constant band representing the year of that image and the precipitation. So when we sample that image at each pixel and the reducer runs, you get a pair of year and precipitation values accordingly. One other small change, you can see when you create an image from constant, the data type becomes double, that is a floating point values. And since our year values are integers, we can, it'll help our analysis if we just cast it to integer. So there's a function called toShort, which will convert this data type into an int16 data type. So when you work with integers, it's recommended to use that particular data type. So we converted this from double to int16. This also helps with our charting and other things. So we have this two-band image collection that we have created from our source collection. And now we are ready to run our reducer. But I want to pause here and see if there are questions. If you want to do trend analysis with a single year, you need to have a trend in a single year. If you say I have a trend in a single year and I have multiple images, then you can do trend analysis. So trend analysis can happen on a time series. So if you take your chirps data, you have pixel values or you have observations every 5 days. If you say I want to take a yearly trend, take all this 5-day interval precipitation, and I see a yearly trend of something, well, you can do the same thing with the yearly data. But typically you don't, precipitation doesn't have a kind of increasing or decreasing trend within a year. You're comparing year-to-year trend. So we are first creating a yearly time series. So we have 40-year time series of yearly rainfall, and then we are fitting a trend to that. trend analysis can be done only with image collections. Right? So you are doing per pixel trend, and each pixel you have multiple observations, and then you can do the trend. Okay, we have the collection. Now we'll create the sense loop. So we have a reducer, EE reducer sense slope. This is a 2-input reducer that computes the sense slope estimator. The inputs are expected to be X data followed by Y data. That's why we ordered our band so that the first value is our X axis for trend, which is the year. Second band is the Y values, which is the amount of precipitation for that year. So we have this 2 inputs as 2 bands, and then the output will be a slope and offset. We run the reducer the same way we run other reducers. So we'll say take a collection dot reduce, and we give the reducer. What will be the data type of the sense variable? Can anybody guess? When you run a reducer on an image collection, what do you get? We have an image collection with 2 bands. We run this reducer, we get an image. And this reducer generates 2 outputs, slope and offset. So we'll have a 2-band image as our output. So let's run this and see. So we have an output where we have 2 bands, slope and offset. And this is a global image with the trend, a 40-year trend at each pixel. The most important output of this is the slope. So let's just select the slope and visualize this. So we select this, and now we can visualize this. This represents the yearly trend in precipitation. Since our x-axis was the year numbers, right? So we had year values at our x-axis. So whatever the output is there, it's the slope of the line per year. So if the output is 10, that will mean that it's a 10 millimeter per year increase. If the value is negative 20, that means negative trend of 20 millimeters per year. Since it's a trend, I think we can visualize this with minus 10 to plus 10. Let's see how the result looks. And we can have a palette. I'm going to use a diverging palette. We'll do brown, white, and blue. That means minus 10 will be brown, plus 10 will be blue. The middle it will be white. So we can visualize the results a little bit better. So let's add it to the map. And now we have this image showing what is the trend of precipitation over the last 40 years. I can inspect the pixel value, go to inspector, can inspect here where I see brown. It says slope is -9. So at this pixel is experiencing a negative trend of 10 millimeters per year. This region is experiencing 12 millimeters of increased precipitation year over year. We can also validate this data. One trick to just check whether this whatever analysis was correct or not is we can actually add the collection yearly call to the map. And I don't want to visualize it. So I will want those values to be there when I inspect it, but I don't want to see it on map. So the add layer function has one more parameter shown, where it'll be shown on the map or not. So if you want to just add it to the map but hide it, you can set this 4th parameter to be false. So when I run this, you can see my map, the layer is there, but it's hidden. So now when I inspect it, I can actually see the time series. So if I inspect this, you will see that this is my time series. So now you can see this is my yearly, on x-axis I have year, y-axis I have precipitation. And this is about -8 trend. And I can see that trend, right? I can see that there's a decreasing trend of precipitation here. Similarly, if I click somewhere where there's an increasing trend, I can see that time series here. This is a good visual check to say my code is correct or not. You have a feature collection or image collection added to the map. When you inspect it, you get a chart of all the pixel values. So you can see when you inspect it, you get the top value, which is the topmost pixel, but you have the full series here. So you can see the individual values, or you can create a chart. So this is a feature of the inspector and quite helpful to kind of visually see the trend. A few questions: could this method be applied to other indices such as NDVI as well? NDVI is tricky because NDVI also has an intra-annual trend, right? NDVI is more of a harmonic trend. So if you want to apply similar technique to NDVI, you would apply the harmonic trend. Let me show you. So this is the video that I've linked to. There is a slide. Let's just look at how do you fit a trend line to an NDVI time series. And this is the example here. So you can see I have a Landsat 8 NDVI time series. I want to do some trend analysis. So the first example is just fitting a linear trend line. So you can fit a linear trend line to it. So similar to what we did. So if you just say, I have this time series, assume there is only one trend. There's only a linear trend. So you fit a linear trend line similar to what we did, and you get, is the NDVI overall increasing or decreasing? But what you really want to do is not fit a linear trend line, but fit a harmonic trend line. Because you have this harmonic model, NDVI follows this kind of cycle throughout the year. So you fit a cyclical curve to it, you can estimate the trend much better. So again, the video explains all the theory behind it. Again, you don't really need to understand the theory. When I need to do this, I will just copy the code, paste it, and I have a harmonic model fitted to my NDVI time series. So you can see this curve that you get. This red one is the harmonic model that you have fitted to that. And that model will be in form of per pixel bands. You get amplitude and phase bands at each pixel, which is representing this harmonic trend at each line. Right? And you can kind of show those trend on the map. So if you want to show this harmonic trend, you can visualize this in a different way. So this is again a very powerful technique. We have, when we cover supervised classification, this is a very powerful technique to capture the phenology of each pixel and add it as an input to your classifier. So you can take this trend in terms of the phase and amplitude bands, add it to your image, and use that for your machine learning model that will look at the trend at different pixels. That means there are two crops growing at two farms which have a different cycle. You can separate them apart because they'll have a different model fitted to it. More modern methods people have done is for field delineation. They take this, visualize this, export this visualized image, send it to the Facebook SAM model, which will segment this into farms. Right? So again, you can use this as an input to your segmentation model, which you can generate from here. Can we know the intersect value with y-axis? Yes. So you just do, you can see this one has slope and intersect. So just select the intercept band and you'll get the per pixel intercept at that as well. So we built the script to do trend analysis. Let me try to explain it in a different way so to help you understand this. We had to take our yearly precipitation dataset where we had at each pixel the value of precipitation for each year, and we would do a trend analysis. And to do this, we had to create this two-band image and run the reducer. Now, to understand why we needed a two-band image, let me give you a much simpler example. So I'm going to comment out everything else we have. So let's say we want to find the trend for the following data. So trend, it makes sense only with time series data. So you need X and Y values. Here's some X values and Y values, and you want to know the trend of that. So let's say we have this pair of values, 2000 and 10. So we have X equals 2000, Y equals 10. That's the first pair of values. Second pair of values will be X equals 2001, Y is 20. Third value is X equals 2002, value is 30. Fourth value is X equals to 2003 and value is 40. Now imagine X is the year and Y is the precipitation. You can easily see the trend, right? What is the trend? You can see that the trend is an increasing trend of 10 per year. And we can kind of visually easily see that. Can we, now, if you want to use Earth Engine to do this, we know there's a reducer called sense slope that can do this. So if this was a value at each pixel, and we can run a sense slope reducer, this when we get the trend output. So let's just create the data. So right now we're just going to create a list because we just want to have a single set of values, and we can run a reducer on list as well. So I'm going to create this list like this: 2010, 2001, 20, 2002, 30, 2003, 40. Right, so we have this list of lists which represents our data. And when you run this sense slope reducer on an image, this is what happens at each pixel. You get pair of values, X followed by Y. This is what the sense slope reducer expects at. And now we can say data.reduce, reducer sense slope. It's a reducer. It can be run on a list as well. It could run on an image collection as well. So we try running it on a list. Let's print the trend. You can see we get a slope of 10. Right? This is what the sense slope output gave you. So this is what's happening at each pixel of the image. You have a multi-band image, and at each pixel, you get this pair of values from those bands, and you get the slope at each pixel. So to do this at every pixel, we have to have images. We already have images for precipitation. We don't have images for the years. That's why we have to create a constant image and add it to each image, so that when we take the value of each pixel, we get pairs, not just a single precipitation value, but the pair of year followed by precipitation. Hope this helps you understand what's happening with the reducer a little bit better. Let's do an exercise. Victor, you can explain.